Okay, warning, this lecture is being recorded. You may want to turn off your webcam if you do not wish to appear in the recording. It's also, I'm obligated to give you that warning. Okay, so what I want to do today, so once we return from the break, the course material is going to get a little bit hectic, a little bit heavy. So once we get back from the break, we're going to be doing functors, applicatives, monads, and state transformations. That gets a little bit tough. So today, I'm going to give you a lecture which is basically for the sake of completeness, and there's only like really one topic today that you really need to understand in terms of like getting tested on. So it's broken into two pieces. I'm going to talk to you a little bit about Haskell testing and HSpec, which is the unit tester, which I don't really care about. I just want to show it to you for completeness. Then we're going to talk about QuickChecks, which is something that I do care about, and I am going to test you on. And it's quite interesting. Haskell, have you guys done QuickChecks before, or property checks? Haskell is the programming language that actually pioneered this approach of quick checking or property checking. So it'd be a shame not to show you how it works in the system. That's the second part of this lecture. The first part of this lecture is going to be on maybe, either, and sort of, do you know what it means to signal adversity? It's sort of like when we need to throw errors and raise errors. So this is going to be a little bit problematic in a functional programming space, right? Because we want to throw errors in such a way that our functions still remain total. Like I want to be able to say something went wrong, but still have my function be total somehow. So we've seen how to do this. Like you've maybe, in some of your exercism problems, have engaged with this maybe data type, where you can say divide 1 by x, and that maybe gives me an integer. Now, the difficulty with using maybe, or either, or any of these other techniques we're going to find, is that it like really pollutes your code with like all of these decorators, right? You have maybes everywhere, you have jests. To make matters worse, if you were to like embed these functions, like then you have to write 4 pattern matches, 8, 16. So introducing maybe and either is really going to make our code a lot worse. But then introducing functors and applicatives are going to fix everything. So I sort of have to show you today how to use maybes and eithers so we can like fully appreciate what functors and applicatives are doing. Because if you think of what like raising an exception does in like the imperative space, there is something that's like pushing the error up the chain. Like if you have a function which calls a function which calls a function which errors, that error gets lifted all the way back to like the function you invoked it from, at which point you could try catch around it. We're going to have to come up with a similar mechanism of like bumping sort of what we're going to call errors, like up a chain of functions somehow, in such a way that our functions remain total. I think there is a slide missing. Oh, okay. We should strive to write total functions that do not bottom out or stop execution of our programs. However, it's not always possible to ensure our functions terminate in general. For example, it is trivial to create a semi-decidable problem because we have streams. So I can say foo of empty is false, and foo of x's is, if x is 0, then true, else foo of x's. So what I'm doing is I'm just searching this list for a 0. So as we know, if I call foo on -10 to infinity, that's going to return true, right? Because it found a 0. However, this is not going to return a 0, and I know this irritates you, so you can try to solve it somehow. This is bottoms out. This is undecidable. So, like, no matter what we do, we're never going to be able to like prevent non-total functions from occurring, like simply by trying to type them out of the system. So let's focus on decidable problems only, and then insist that decidable problems at least have to be total when we rewrite them. So a decidable problem is one that terminates on all input. And let us ensure these never cause termination to halt by throwing exceptions, by having them signal adversity instead. So we can signal adversity by using the following things. So we can use this sort of maybe data type. So if we add nothing to our type, whenever we do something bad, we can just sort of throw nothing. Either is a data type that lets you combine 2 data types. So it's sort of like a union operator. We can use smart constructors to actually like prohibit the instantiation of like ill-formed data. And then I sort of want to discuss kinds. which is sort of like a super type of the type classes. So there's like one more superset that we have to discuss. Okay, so let us recall again the definition of a data constructor for maybe. So here it is. So maybe of A is either nothing or just of A. So maybe is the standard way of signaling a computation has failed because you can just return nothing in the case where something bad happens. So let us write a tail function, which is a non-total function, as a total function. So recall that tail is a function that, given a list, returns everything that's not the head, right? All lists are broken into head and tail. So notice here, if I call tail an empty list, that we're going to get an exception. So how can we write tail so that it's a total function?
We can say that the tail of an empty list is the empty list.
But that's not really true, right? So you're recommending using a default value, which is appropriate in some cases. But then tail of a unary list and a tail of an empty list would be the same. And that's sort of like not really expected.
So nothing then, I guess.
Yeah, so we want to write a function that, for tail, that returns nothing when given the empty list. So this is sort of like better than using undefined. Because if I were to say tail of empty list is undefined, as soon as you call tail of empty, undefined stops execution. I can't like pattern match. I can't say if tail empty is undefined, do something. But I can say if tail empty is nothing. So here's what I can do to get like a safe tail function. So safe tail takes a list of A and it goes to maybe list of A. And as I recommended, safe tail of empty can be nothing. And safe tail of x's is just, and then call the usual tail, right? Because if I wanted to recurse on safe tail, it gets kind of messy. Maybe we should do that just so I can show you how introducing maybe really screws things up. Okay, so here we have safe tail. So just to see, that gives us 2, 3. And safe tail of empty gives us nothing. But let's try actually programming this so that I don't actually call tail. So safe tail is what? Takes a list of A and goes to maybe list of A. Safe tail of empty is equal to nothing. So this is what I want to say now. Safe tail of x's is equal to, how do I want to say this? Because it's not going to be, it's just going to be x's. Just x's, yeah. Oh, so that wasn't too bad, actually. I think that I should probably switch the slide. Yeah, this is wrong, actually, as written. I shouldn't be returning. Oh, no, this is fine, because I'm pattern matching x's against x's. So either implementation is fine. I actually think the one I just did is a little bit better. But the point is, we're going to use nothing rather than using undefined. But that's sort of, it's going to make things a little bit more difficult to pattern match against, because everything that is returning is now going to be wrapped with a jest constructor. Design a data type for representing students as entities that have names, strings, and student numbers, integers. Return nothing when instantiating a student with bad input. Okay, so now that we have this maybe data type, I have a way of like creating data and like making sure that data is valid when entered. It's okay. You should see kind of the stuff that happens in the other class. I can occasionally trigger people's series in Google's, and it's like real funny. Do you guys know what an Amber Alert is? Okay, so when I was teaching in Canada, like we had, an Amber Alert is a alarm which the government can trigger on your phone. And like it overrides like any silent settings that you have. So it's like
In Australia?
In Canada.
Okay.
So it would happen semi-frequently when I was in lecture that they would send out an Amber Alert and like literally 100 people's phones would like become an alarm. Or this thing would like go off at 4 in the morning. It became kind of irritating. Because it's like, what do you expect me to do? Like get out of bed and start like looking around like at night. But in any case, okay, so now that I have this nothing, we can create data and validate the data is valid and return nothing when it's invalid. Suppose I wanted to create a data for a student and this student had a name and an ID, and like suppose I wanted to like validate the name didn't have like sort of non-ASCII characters, or like suppose all names had to be constructed with lowercase and uppercase letters and rejected everything else. And suppose IDs were only supposed to be like 8 digits long. And suppose further that I never want a student object that like never passes those types of conditions. How do I sort of implement that in Haskell? So here's a student, Bandit Healer, 1, 2, 3, 4, 5, 6, 7, 8. And this is a student that's well-formed. Pardon me? Oh, so maybe it's not well-formed because I put a double. Why is this a link? That's weird. Yeah, everyone's like, click it, click it. I'm like, no, I'm not clicking a random web link when I'm recording and it's on a projector. That's just begging for something bad to happen. Okay, I did correct it down there, it seems, though. Okay, but what happens if I want to like not allow that to happen? Well, I can write the following sort of set of code in Haskell. To validate a name, now utilizing the fact that we have some sort of higher order patterns. A name is valid only when every one of its characters is either a lowercase letter, uppercase letter, or space, I suppose. And this is an expression which is encoding exactly what I just said. A name is valid when all the elements from that name. Am I doing a map here? Okay, let me look up all. I thought, again, this is probably something me getting confused between Haskell and Python again. Oh, it's a foldable. Okay, yeah, so I need to do something like all greater than 0. Oh, sorry, thank you. Right, okay, so this does make sense. So I'm saying all the characters of name have to satisfy this predicate, and this predicate says that the character has to be an element of lowercase letters, right? The lowercase letters A through Z, or the uppercase letters A through Z, or the space. Okay, so this is like trivially going to validate names, although I suppose it's going to accept the empty character. So like maybe I should be a little bit more clever with how I validate names. But yes, sir.
Are we going to be using rejects at all in this course?
We're going to be using rejects at all.
Yeah, for validating strings.
I don't know what a reject is.
Lego expressions.
Huh? Oh, regex.
Rejects.
I thought you were talking about like rejects as in like rejected people. Like, okay. No regex. Like unless you want, but I'm not going to give you crazy patterns to match that would require them. Do all of you know regex expressions? Or all of you know rejects, I suppose? Yeah, kind of. I thought you were tossing me throw balls about like, you know, are we rejects? Like a student? Never mind. Okay, so how do we validate a name? We did that. How do we validate an ID? Well, we just need to check that the ID has 8 digits, which is easily done by just taking the base 10 log. Although you have to be a little bit careful here. Because log expects something from like the number type, and I don't think that it can take like just an integer. So you have to, from integer is a something in Haskell that takes an integer and like promotes it to number, right? So it could be treated like a float, because you can't really cast from integer to float. You can sort of cast from integer to number and then number to float. Like you have to go up and then back down again. You can't really go across. So if you ever have difficulty like applying some of these base operations like logs or lons, just be careful about its type. You have to sort of move up to a number by using this from integer. But in any case, it's like very easy to see that I tricked my students last year. I had them write a verifier for credit card numbers, and the first line of it was, credit card numbers are positive numbers with the following restrictions. And many of the class didn't check this condition, right? The credit card number has to be bigger than 0. So I think that was just me trying to reemphasize that lesson. But here, yeah, like we have to check, like there could be 8-digit negative numbers and we want to reject them. So to validate an ID, I want a positive ID, and I want the floor of the log base 10 of the from integer of ID to be 7. So this basically says bigger than 0 in 8 digits. And then I can sort of make what is analogous to like a constructor in Haskell, call it makeStudent, which given a name and an ID, returns maybe a student, right? Because now that this is a constructor that's validating something, it's always possible that the validator is going to fail. So I can say make student with this name and ID, and if I can validate the name and I can validate the ID, then return just student name ID, right? And this is the type of pollution that I am talking about, right? Because now to get name and ID out of this, you have to do 2 pattern matches. You have to pattern match the jest out, then you have to pattern match the student out to access name and ID. And in fact, a functor is the thing that lets you like go inside the jest and do stuff without doing that type of stripping. Right, so again, one of the reasons I'm showing you this is simply so you can have an appreciation for functors and applicatives next week. So this is just how it works in action. Make student, bandit, healer. I think that one will validate. Yep, so we get just a student, bandit, healer, 1, 2, 3, 4, 5, 6, 7, 8. I can make a student, bandit, healer, 1, 2, 3, 4. And what do we expect happens here? Yeah, we just get nothing back. Make student, bandit, bash, healer. What do we get? Nothing. Okay. But what if we want to actually like signal why these things have failed? Right? Nothing's a little bit useful. Like at least now we can like write code to like sort of try catch around this. But it'd be good to like get more informative type of information about like why a constructor failed to construct something. So this is where the either data type becomes relevant. So maybe is simply sort of adding nothing, like one extra element to your set. You have everything in your type plus nothing. Either is the constructor that allows you to take 2 types and like union them. So I can say, here's the data constructor for either. So you have data either, and it takes 2 types, A and B, and it constructs left of A, right of B. I know this is kind of weird, but it's sort of like the thing on the left side of the union or right. So I can have either int or string, right? So now we can, because like at this point, were you able to have a function that returned either an integer or a string? Would that have been possible? No, it wouldn't have typed out. You could have made some sort of super type that collected both integers and strings in them, but that's sort of different and basically equivalent to what we're doing here, right? So either is going to be, among other things, a tool that's going to allow you now to like return one of 2 types from a function. For instance, we can write a function that takes either an integer or a string and returns a string. So here we have convert. It's either an integer or a string that you're taking as input, and I'm going to return a string. So convert left of m. So left is going to be something that's an integer. So if it's an integer, I'm going to just show it. That converts it to a string. And convert right of x's. So that means that like this is going to be a string. I just then return that string. Yes, sir.
Not either. Can you do more than 2 elements, or is it restricted to just...
Well, you can like recurse on the eithers, right?
Okay.
So you can have either A, either B or C.
Yep.
But then like that's going to be horrific to unwrap. So yeah, in some sense, I'm introducing a bunch of solutions that are like just creating a bunch of problems, which will get fixed after the break. But yes, certainly you can. Yeah, so remember, like whenever I show you like an abstract type, that could be any type. And right, either AB is, either AB is not a concrete type, so we have to pass concrete types. I'm actually going to talk about that at the end of the lecture. So you can't pass either. You can pass either int string, right? Because one is concrete and the other isn't. Yeah. We're going to do that at the end. Okay. So now I can say convert right hello. Convert left 1. Oh, hello. 1. Okay. So here we go. Here's a function that could take either an integer or a string and return a string. Okay. Here's the opposite. Here's a function that takes a string and can return either an integer or a string. So I don't know, like suppose I want to convert like the word 1, the word 2, the word 3 into either an integer or a string. So, and then all other strings just stay themselves. Okay, so I'm going to write a function which only converts 1, 2, or 3 to their numbers, and every other string is going to stay the string. And this is how you would do it, right? So I can say, with pattern matching, converting 1. So the pattern match here is fine because we're pattern matching on only strings. But I say return left 1, right? I'm saying that I'm returning something from like the left of this union, and it's 1. For 2, return something on the left of this union and return 2, and so on and so forth. So convert 1, left of 1. Convert, I hit the keyboard, right. Right, so those are 2 examples. First example, taking 2 data types, either of 2 data types and returning one thing, and this one is taking one thing and returning either of 2 data types. Well, how does this resolve the problem that I was just talking about in terms of not giving reasonable feedback when you're failing constructors? Well, consider that we're always able to like write data, and I can just create like some data for what it means to be an invalid student, and we can put an arbitrary amount of literals in, right? So I can have an invalid student data type, and I can say invalid students are either bad names or bad ints. And then I can say something like, as I said, you can have as many literals as you want, right? Depending how specific error reporting that you want to do. So now we can say, I want to make a student, and it's either an invalid student or a student, right? Instead of saying that it's maybe a student. Okay, so, but what happens if I want to be a little bit more descriptive than what I would be locked into describing in a data constructor, which has to be sort of like one word that's capital camel cased? Don't forget that we can derive instances of classes, and one of the classes that we can derive is show. And in this case, we can like overwrite what it means to show. So I can say, what does it mean to like show bad name? I can say to show bad name actually means to like print this string. Huh? Too many characters? Did I spell something wrong? I don't get it. Did I make a mistake? Oh, okay. In any case, right? So because you wouldn't want to put these like huge long strings in like your data type, that would get kind of messy. You could also like be a little bit more cheeky and have error 1, error 2, error 3, error 4, and then have like a list of what those errors do, right? So this is how you create a constructor, and then some data for signaling errors, or what I was calling signaling adversity. And then this is how you derive an instance of OR to actually flesh out more what these sort of adversities mean. So here, like if your function were to return bad name, what it would actually show is names must only have alpha characters and spaces. And bad ID would just show ID numbers need to be positive in 8 digits. Right? So if you wanted to have error handling in your code, this would be one way of doing it. So this is how I would now implement make student, like using this new data type and an either. I could have make student, which takes a name and an ID. Name is just like a type synonym for string. ID is just a type synonym for integer. But I'm just utilizing them to show you how it like simplifies your code. So it takes a name, an ID, and I can return either an invalid student or a student. And it looks something like this. Now, there is a convention when using either to signal adversity, and that is left is where the error should be. And it's because left isn't right. So your errors aren't, this is literally the reasoning behind doing this, right? An error is wrong, so it's not right. So that's why right is for the stuff that works, and left is for stuff that isn't right or correct. It's not a bad way of remembering how to do it. Well, yeah, it's not, doesn't have any sort of functional difference, but it is a convention that they did. So make student, if it's not a valid, if we can't validate the name, then I should return left bad name. If I can't validate the ID, I should return left bad ID. And otherwise, I can return right of a student object. So I can say make student bandit healer, And it says, no problem, right, student, bandit. Oh, there should be a healer there. 1, 2, 3, 4, 5, 6, 7, 8. I can say make student, bandit, healer. 1, 2, 3, 4, 5, 6, 8. And what should this trigger? Left, and then it shows sort of the full. ID numbers need to be positive in 8 digits. What about this one? Well, this is sort of what I'm trying to get at. This violates both. So what's going to happen here? It will be the first thing, right? Because this is one of the, in guards, that's one of the instances where order has to matter. So in fact, when this got passed to make student, this triggered first. Okay, so as an exercise, I want you to modify the code so it returns all of the relevant errors, right? Instead of just like the first thing that's wrong. Perhaps you want to return like a list. It should be either a list of bad student or a student. Okay, so now getting back to what I sort of was alluding to in terms of if we can pass either to either or maybe to maybe. So now we have these type constructors that are like higher kinded types, because there are types that take like other types before they can become types. I know I just said the word types quite a bit, but like we have some types that take, so like the list type is a type that needs an integer before it becomes a type. And the same is going to be true about these maybe and eithers. So we have this notion of a kind, which is a superset of types. So you have all these types, they're sort of concrete types, and then you have a kind, which is a larger collection. They're used to describe the types of type constructors. The inclusion of higher kinded types in Haskell is considered a noteworthy feature. Like I think not many languages have something that's even higher than a type or a class. So a pointer in asterisk is a symbol designating the set of concrete types, right? So a concrete type is a type that is doesn't need another type to start working. Yes?
So the high concrete types, in what way are they more advanced than generics?
I don't want to say more advanced. I'm just saying, okay, so let me go through this slide, and if you still have the question, I'll try to address it again. I'll just have more nomenclature to address it. Okay, so the kind of int, it's concrete, because int doesn't need another type in order to be a type. Agree? It's just the integers. Kind of bool is concrete. It's like literally 2 data constructors, true and false. Kind of char is concrete. So usually we read these double colons as has the type, but here we're sort of reading it as has the kind. All right, so there's a sort of difference between kinds and types. Okay, one more slide. So suppose now I have data for animals, and animals is a new data type that takes a dog, but dog needs to take a string, or a cat. So what's the kind of animals? It's concrete, right? It's fully done. What about data for a tree, which accepts a type A and then constructs a binary tree of type A? It needs a concrete type in order to become a concrete type. So can this answer your question? There has to be something higher than types that are designated by asterisks, because there are types that are sort of more general, because it's like a decorator over a type, or it's like a type that can only become a concrete type once. So because like there's trees for integers, there's trees for characters. So where should like the tree framework live?
It doesn't seem any different to a tree or list in C# or Rust, doesn't it?
So I can't remember. Would you be able to just instantiate a tree in C that can take like any type in its nodes?
In C#, yeah.
Okay, I'm not very familiar with C#.
Or Rust, or any language with generics.
So maybe this is equivalent to generics, but this is just sort of how Haskell chose to sort of implement it. It's not sort of a value judgment, it's just sort of is what it is. It decided to collect, because like we do need some type of distinction between a type that can't become a type until it's given something and the concrete types. Because we now have, because I just said you can pass either to either. That's not really true. You can pass a concrete either to either. So I have some examples like this. We'll go through. Oh, so what's the kind of maybe? Answer a question. Question, okay.
It's semi-unrelated, but with the data animals constructor at the top, does that mean that dog accepts the string, but cat doesn't accept the string?
Why name a cat? Why name an animal that doesn't come when you call it? That's usually why this is the example.
Okay.
Yeah. So I could have said probably dog takes a name or cat.
Yeah.
Um,
Could you have said something like data animals accepts a string equals dog or cat?
but then you're constructing nothing over the string. I don't know. We'll have to try. Like ask me again later, and then I'll sit down and think about it. Because like now that I'm staring at this, it's like not even looking right. But it's because I was programming in Python all yesterday, and now I'm totally jiggered up. You may notice I'm not doing much live coding today. I don't have much mental bandwidth at the moment. But in any case, what's the kind of maybe? Right. So in order for maybe to become a concrete type, it needs a concrete type, which means, what's the kind of either? Yeah, either needs to take two concrete types before becoming a concrete type, right? Either takes the union of two types. So now there's some stuff that can happen here. So what is the kind of maybe int? It's concrete, right? You can start using it as a concrete type. What is the kind of either int? Yes, concrete to concrete, right? I need one more concrete data type before I myself can become a concrete data type. What is the kind of either int? Concrete, okay. So concrete types are the only types that we're actually able to work with. Okay, so now I want to know if I can pass like certain things to maybe and either. So what is the kind of maybe int? Concrete, right? Because maybe goes from concrete to concrete. You give it int, which is concrete. So this becomes concrete, which you pass to maybe, so the whole thing becomes concrete. So this means that, yes, you're totally allowed to pass this. That this totally can be in the type signature for a function. Kind, either, maybe int, maybe string. Concrete, right? Because this is concrete, and therefore either is concrete. So no problem passing this, or no problem using this as in the type signature of a function. Kind, either int or string. Concrete to concrete, right? It says I still need one more concrete data type before I can behave as a concrete data type. So therefore, we wouldn't be able to use this in a type signature, which gets back to what, Sir, you were asking at the beginning of the lecture in terms of passing either to either. So this is me passing either to either. I just need to put like one more concrete data type needs to be there. So strictly speaking, I can't pass either to either. I can pass like either int to either, but I can't pass either. Oh, here's a good what's the kind of maybe? Error. Right, because you're trying to, it's saying I take concrete types to concrete types, and what you've in fact done is passed maybe an abstract type or a higher kinded type, non-concrete type. So just keep this in mind, right? That you have types and you have kinds, and there's like a little difference between them. Determine the kind signatures for the following type constructors or indicate that an error will occur. So this is just a bunch of exercises that we're going to do before we move on to the second lecture. So what's the kind of empty list? It's a concrete type. Oh, it's an empty list. Oh, Lord. This is the type constructor. I think this is why I use this as an example. This is not the empty list. This is the constructor for lists. This is why people don't like using the syntactic sugar for this reason. Like I think I can do something like I shouldn't type there because then the chat can't see it. I should be able to do like type construct over int. Oh, but that's not going to do anything. Yeah.
Can you do a more generic list, then take a variables?
Yeah, I can do this. What's the kind of the list constructor? And it's a kind to kind. I think that's actually literally what's in the slides, right? So that's not empty list. This is the list constructor, and it looks identical to the empty list, which is why Haskellians sort of get cranky about that syntactic sugar. Mathematicians are sort of allergic to ambiguity, and this was an ambiguity that was needlessly introduced. Oh, yeah, so here, kind of the list constructor taking an int is a concrete type. This is a concrete type. Oh, that's an error. So kind of, you can't, why couldn't I have taken maybe over the list constructor?
Because you need to give a concrete type to maybe.
Right, because the list constructor isn't concrete, right? It's waiting for a concrete type to become concrete. So would this work?
Misspelling, but yes.
Modulo my misspellings, it works. Yes. Oh, that wasn't a hint. Sorry, that was just a stretch. It's good to stretch. So here's some homework exercises for you to try. So given the identity function, what's the kind of a, write the factorial function that returns nothing if its input is negative. Given R that takes a concrete type and just sort of decorates it with F, what are the kinds of A and F of A? Write a function isJust, which takes maybe A to a bool that tests for the presence of just and some maybe type. For example, isJust of just one is true and isJust of nothing is false. And what is the kind of the application constructor in Haskell? And like, don't look it up first. Try and think about it, then you can look it up. Would you guys like a break today, or you just like to continue going? Keep going?
Yeah.
Okay. I assume that you speak for the whole class, right? Since the rest of the class is silent. You had some type of democratic election. Just give me 1 second to drink a cup of coffee.
So we do need a break. So we do need a break.
Well, sometimes but it's okay. I wasted a lot of time at the beginning of class talking about stuff that wasn't actually course material. So I feel like I owe you. Okay, so really no one needs a toilet break or a cup of coffee or anything. We forge forward. Okay, so that was just sort of like a little technical discussion about maybe an either and kinds. We're going to revisit that when we start talking about functors and applicatives, because again, I introduced a solution that's going to create a lot of pollution and problems, and functors and applicatives are going to help us mitigate that. This part of the lecture, okay, so I do want you to know how to work with kinds. I'll probably have some kind problems on your exam, like what is the kind of this? But really the main thing I want you to learn today is this notion of property checking and QuickCheck. There's actually some quick checks. I asked you to do a couple quick checks on assignment 2. I will certainly ask you to do quick checks on your exam, right? So this is sort of going to be the meat of today's lecture. This is for you to pray. I'll just check in on the chat. Chat, you still with us? Are signs of life out there? Yep. Okay, thank you. Quick check on the chat. Let's quick check on the chat before our quick check discussion. You hate chat? Oh, you hate that? I love dad jokes. Anyone have a good dad joke for me? I'm a dad, so I'm trying to collect them.
Rick Astley will lend you any Pixar movie in his collection but one. He will never lend you.
This joke sucks. Can't even execute it properly, right?
At the end. I got a few at the end.
We'll talk at the end. Maybe you should practice a bit before, right, delivering them. Okay, one more opportunity for a real dad joke. Anyone have a real dad joke? Nice hustle, guys. Think if you have them, maybe I'll start a super thread on the EdStem. Oh, there's 2 in chat. Okay. I'm currently camping, but you still have my attention. Man, camping is intense. Yeah. 2 tomatoes are sitting in the fridge. One tomato says, "Man, it's really cold in this fridge." And the other tomato goes, "Holy shit, it's a talking tomato." Testing is a more practical matter than one of functional programming, but it is nonetheless important for when we actually write Haskell programs and want to ensure, or at least be confident that our software is correct. So what I mean to say here is like, testing code isn't like something specific to the functional coding paradigm. Code testing is something universal to writing code. And I suppose I just want to show you how testing is done in Haskell. Because it's already the case that I've had to do tests on your code that aren't unit tests, that we had to test properties of your code. Because, do you know what a canonical form means? It's not really an order. So there's like this notion in math between the difference of equality and equivalence. And so like, is 13 o'clock equal to 1 o'clock? Well, it's like equivalent to 1 o'clock, but like 13 and 1 aren't the same. You know what I mean?
Yeah.
So like one's kind of like a property that is, I just need to check that everything mod 12 gives me the same remainder. But that's a little bit different than testing if stuff are equal. So this is relevant, right? Because on your homework, I gave you expand and simplify. Expand, I just said get rid of multiplications from this. That doesn't have a canonical form, right? There are many different ways of like removing the multiplications that give you something with additions that is correct. Simplify does have a canonical form, so that one I can do I can do unit tests on because your output should be identical to my output. So a property test of what I can do on expand could be something like this. So for your homework, I'll say, okay, I'm testing student expand. Expand of f should be equivalent to f, and f should have no multiplication in it. Right? That's the type of test I'm going to be able to do on your expand. Whereas on your simplify, yeah, I'm really going to say these two things have to be identical. Right? So you need to know that sort of property testing is a thing, and sometimes it's going to be your only tool for trying to confirm the correctness of stuff. So broadly speaking, testing falls into two categories: unit testing, which is probably the testing you're more familiar with, and then property testing, which is sort of what I've just been describing now. Okay, so what's a unit test? So when we assert a function's output for a finitely many inputs, which are chosen by us, striving to choose edge cases and typical cases, or they're arbitrary, we can do that with quick checking. So suppose I spin up like a trivial function that all it does is take the product of two numbers. Unit testing would be something like me saying foo of 0, 0 should be equal to 0. Foo of 2 and 3 should be equal to 6. And then I write like an arbitrary amount of these until I'm satisfied that I have like necessary coverage of like edges and stuff like that. Like we have domains. So if this was like the positive integers, there'd be an edge of that domain being like 0 or 1. So like usually with quick checks, with unit tests, you want to check zeros, empty cases, units, unary lists, and then some typical cases. I trust that you've done unit testing before. Okay, so this is how you do unit testing from within Haskell. So suppose we have the following trivial function in a module called sandbox. So when I say module, that's basically synonymous with like something in a file. Yes, sir.
That should be a b, right? That should be x times y.
Should this be an x times y?
Well,
Oh, that should be an x times y. Thank you. Pardon me?
yeah, like the tag signature for about.
Oh, right. Jeez. I'll fix that as well. Everything's correct modulo my typos. So this is an x and this is an int. So suppose we have the trivial functions in a module called sandbox. So the important thing is that you interpret when I say module, it's the same thing as file, right? The same thing is true of Python, right? All Python files are considered modules. And this is sort of why we've been sort of naming the contents of a file a module, right? And usually we name the module the same thing as we name the file for this reason. Okay, so in the same directory, you want to create a file called sandbox spec. It doesn't have to be called sandbox spec. This is just sort of the convention that we use to signal that this is the file that is going to test another file. And in this file, you want to do the following things. You want to import the file where the functions that you want to test live. You want to import test.hspec, which may require you install this. Are you familiar with Cabal or Cabal? So when you installed Haskell, you should have got access to Cabal, which is the package manager for Haskell. We're not going to be really using HSpec properly. I'm going to show you how to hack it into the system. But first and foremost, you should make sure that it's installed. Okay, I can't really explain much of this before we talk about monads. But suffice to say, I'm eventually going to show you how we can utilize univariate functions to sequence actions. And we're going to utilize that through this do interface. Right? Do is sort of like a syntactic sugar for calling a sequence of functions that is, for calling a bunch of functions whose purpose is to sequence something. Right? So everything in these do's are sequenced lines. So I want to create a main function. Now, something else you should bear in mind is that if you create a main function in Haskell, the main function has to be of type IO. And then from the REPL, you can type run Haskell on the file, and it will automatically run what's in main. Right? So as a matter of fact, you can't actually define main in a Haskell file and have it be anything else besides this type OO. Main's almost like a keyword. It's the thing that run Haskell is going to look for when executing. So I can say, okay, so what's the main thing I want to do when testing? Well, I want to run HSpec, which is the tester, and I want to do a sequence of tests, and I want to do one thing for each function that I want to test. So I had two functions in that file before. One of them was foo, one of them was bar. So I want to create a description for foo, and I want to do 2 iterations, and in each iteration you want to write some type of description of your test, and then you want to make some type of assertion in your test. So you may have been seeing these assertion errors when you incorrectly submit to MyPyTutor. And it's funny because it's actually sort of reporting backwards. Right? I don't know if you've noticed this when it says this is our expectation. I forget how it's phrased, but the way that it's saying it, it almost makes it seem like your thing is right and our thing is wrong. Like if I said write the identity function, and I tested that, and you wrote it wrong. You said everything was empty. I think the MyPyTutor was saying, I was expecting 1, but got empty. So the expectation is the thing that your function is returning. And the other thing that I was expecting was the correct answer. Anyways, maybe once we flesh this out, it'll become a little bit more. It's a weird error reporting because Haskell was sort of shoehorned into the MyPyTutor system. It wasn't too easy to get it in there. But in any case, if you just follow this framework, and I don't care too much about you knowing how to do unit tests. These aren't the interesting ones. I just want to show you how we're doing some testing on our side. You just have to call this HSpec. You have to have one description for every function that you want to test. And then, so that should be foo. And then you just do an arbitrary amount of should be's. And so this is sort of unit testing in Haskell. Okay, so this is my bash. So I'll just show you simulating my bash. So suppose in this directory I had 2 files, sandbox.hs and sandbox.spec. The 2 files I just shown you without the typos. I can say run Haskell on sandbox.spec. You should have run Haskell in your path somewhere. It should have installed automatically. And what this is going to do is it's going to look for the main function in the spec file, and then execute it. Why then do you reckon it had to have the IO return type?
So that it can actually what?
Well, something needs to be displayed here. This is Unix, right? So Unix philosophy is text in, text out. Right, so when I do this, Unix is really expecting that some string is going to be pushed out, some IO. It's expecting the IO pipe to be passed to it. So therefore, main had to export IO just to sort of fit into the, how else am I supposed to show something if not through input output?
Is this the same as stack test?
Okay, so yes. So there's something in Haskell called the tool stack, and I didn't want to teach it.
I'll just figure it out.
You can do stack test if you want. Well, you can read a little bit about because the tool stack is more for like creating Haskell projects, and it like creates like a lot of directories and stuff in here. So if you want to learn about it, but I just remind you that, like I said from the very get-go, my objective really isn't to make everyone Haskell developers. And truly today, it's just the quick checking I'm getting interested in. But in any case, when you run this over Sandbox, you're going to see output like this. It's saying I'm testing. Okay, this is the test description, but you should put something like testing foo or like checking the right zero. And it's going to say I finished all of this in some amount of time, and for 3 examples, and I had 0 failures. And I believe if you have colors set up in your bash, that should be green, and it will be red if you get any failures. Okay, so about importing test.hspec, we need to talk a little bit about this sort of should be function that I'm using. The type of should be, it's given something that's showable and an equality type, or sort of given 2 things that are showable and an equality type, I can do a comparison on those 2 things and return an expectation. An expectation is just a little bit more sophisticated than like true false, but for these unit tests, we really only care about like, we're asserting that 2 things are equal. Suffice to say, there are more expectations that we can assert. We're just sort of not going to go into them. So what's the kind of expectation? Well, it's just another concrete data type that you can look up the info for. Okay, so that is unit testing, not very interesting, stuff that you've already done. Okay, the interesting thing is property testing. So property testing checks formal properties of programs by expressing some proposition or property that a function must satisfy. And this was pioneered in Haskell, and this is why I sort of feel an obligation to at least show it to you, right? Because it was something that really Haskell was doing first. Now, when we start talking about functors and applicatives and monads, we're going to have to write class instances, and those class instances are going to have to satisfy certain properties. And we can quickly check that new functors and applicatives that we create have these properties by using quick checks. In fact, this is the true purpose of quick checking, is to give us a quick mechanism of verifying conditions are met. But for example, here's a property of reverse that we could check. So I could say if you want to reverse the concatenation of 2 lists, that should be equal to reversing the second list and then concatenating the reverse of the first list. Right, so can you see how this is sort of different than like a unit test? I'm asserting something about the property of the function that we wrote that should be true if we indeed wrote the function correctly. Now so here are some common properties. Normally, so I don't really count these. When I ask you, I'm going to say something on your homework like give me non-trivial quick checks, right? So there are some trivial quick checks, like if you have an identity operator in your domain, like something that's acting like 0. Obviously, you can have a quick check. X plus 0 should be equal to 0 plus X should be equal to X. Or the same thing's true of like the multiplicative identity or the multiplicative 0. Like those are sort of freebies. A lot of the time, idempotence is something interesting to check. That's a function that when you apply it twice, is the same thing as applying it once. Can you think of any functions that would have that property? Yes, sir. Sure, but the identity function is going to trivially like satisfy like all properties. So can you give me something less trivial? But like I have to say, that's the best answer. Whenever I say give me an example of this, yeah, give me the most trivial answer that you can find. So that's a perfectly fine answer and the best answer to give in an exam, but perhaps not something that's like very exemplary, right? So
You've got like projection and dimension.
every year someone says projection. Okay, so do you guys know what a projection is? It's like when you remove one of so you have like a tuple and you like delete one of the tuples. So like suppose you have a triplet and I just like make it a pair.
Well, I mean like put a 0 there, otherwise it won't type correctly.
Can we give like, how about sort? How about something from the computer science space? No, sorting generally. Quicksort is an implementation of sort. Does sort satisfy this idempotence property? Does sorting a list if I sort the list once, is it the same as sorting the list twice?
Yes.
Okay. Involution. This is basically if you apply the function twice, it's sort of like you go in a huge circle. So can you give me an example of a function for which involution would be true? How about something from computer science, right? And it's certainly not derivative, right? Right.
Specific cases, sorry.
Who said reverse?
Someone with that.
Perfect. Thank you. Reverse. Reverse is the best answer. If you reverse and reverse again, you should get the thing that you started with, right? So idempotence and involution are always two things that you should sort of try to look out for. So nothing's really stopping us from doing sort of a property check using like the unit tester. And sort of we could sort of do it like this. I can sort of say, well, here's my property. And it like should be the case that this is equivalent to this. But like, why is this sort of like not great? Like, what do we see here that's generic or arbitrary? Was it the case that my selection of x's and y's mattered? No. Our selection of x's and y's should really be arbitrary. Like, I want to be able to say, check this property, and it should be true for like any lists that you choose. So choose like 100 of them, and let's see if that actually works. So QuickCheck is a provision in Haskell which actually provides you access to the higher kind of type arbitrary. So I can say something like QuickCheck, give me 2 arbitrary lists, and then determine if this property is true, which is pretty cool, I think, right? And the way that it's picking arbitrary elements, it's clever. It includes, like, it tries to include edge cases and base cases, and it typed properly. I didn't have to tell it that x's and y's were of the list type, because the type inference engine can sort this out. When I'm asking for arbitrary things, and I'm making them inputs to functions, Haskell knows, oh, he wants an arbitrary list, or an arbitrary string, or an arbitrary integer. So let's talk about quick checking. So QuickCheck provides access to the arbitrary type class. Because we're not using the tool stack, we have to hack QuickCheck into our code. So I just need to be very upfront. This is definitely not the correct way of using QuickCheck, but it will nonetheless allow us to play with it. I just want you to be able to execute a QuickCheck from within Haskell. So if you get errors about not being able to find QuickCheck, you have to load Haskell by telling it where the QuickCheck package is. So you just have to give it this one command line option. So the first one here is if you want to run QuickCheck on a file. And the second one here is if you want to write, if you just want to launch into the interactive mode of Haskell. So you may or may not get complaints, and this is how you resolve it. So I can launch into interactive Haskell by sort of saying, get this package QuickCheck. We get in, and then I can say import test.QuickCheck, and now I should have access to QuickCheck. So here's a simple QuickCheck, right? Checking commutativity. I can say, give me an arbitrary x, and x times 1 should be equal to 1 times x for any data type that provides multiplication. And then it will spit out something like, okay, you passed 100 tests. I can QuickCheck the associativity of addition. And we're going to be using QuickCheck in this manner a lot when we start doing functors and applicatives. And this is going to say, okay, you passed. I can sort of make sure that, or I can try to test that exponentiation is associative. However, what is the case? Associativity, there is no associativity on exponentiation. So what should I expect for the test to do in this case? Fail. Okay, so let's see how it fails. Failed. And it failed after 1 try, and it's saying, here is your failure case, 0, 0, 0. So let's confirm. What is 0 to the power of 0? 1. What's 1 to the power of 0? 1. What's 0 to the power of 1? 0. right? So 1 is not equal to 0. So this is handy, right? It says you failed, and in fact it gave you like the counter example to why it has failed. So if I ever give you a question and it's something along the lines of, tell me if this statement, tell me if this expression in Haskell is true, and if it's not true, provide a counter example. You can just spin up QuickCheck and have it give you that counter example. Yes?
How do we know what like type it failed on, like whether that's a float or int?
Oh, that's a good point. But I suppose this would just say I'm 0 the number. Right? If you asked for the type of 1, it's going to say it's a number. So it's saying this is going to fail for all of the zeros, right? The float 0, the int 0, right? What are some quick checks that we can write for reverse? Okay, so here was one of them. Any other ideas for some properties that we can quick check on reverse? And you can use like other functions in this case. Although like now we got into this problem of like we're writing quick checks with functions that also need to be quick checked. But that's just the way of the game, right? So
Reverse associative.
is reverse associative? Sure, we could check the associativity of reverse. Yeah. Anyone else?
The length is the same.
That's great. Yeah, the length should be an invariant on the list. The length of x's should be equal to the length of the reversed list. Anything else?
You should have all the same elements.
All the elements from x's should be included in all the elements of the reverses of x's. Those are really great. I have some other ones. I'm going to check the involution. That was one of the ones I mentioned. That reversing the reverse of a list is itself. I want to check that the maximum of the reversed list is equal to the maximum of the unreversed list. I want to check maybe that the reverse of xy is equal to yx. Okay, so this isn't the greatest quick check. It's technically a quick check, but it's really just doing like a bunch of unit tests. So I'm showing this sort of as like a bad example. If I say give me a non-trivial quick check, I don't want stuff like this. I'll usually like bar you from using it by saying you have to use an arbitrary list of arbitrary length, right? You can't just specify what happens on all lists, but you know, technically it would work. I could also say reverse of all unary lists should be equal to themselves, but that's basically just doing 100 unit checks as well. Okay, let's talk about smallest. So what are some properties that smallest must satisfy? And here I actually gave the definition for it. It may be correct, it may be wrong. So I'm saying the smallest member of x's, and my type is a list of int to int, and int is a bounded type. So I'm saying fold r min, which is a bivariate function which given two inputs returns the smaller one. Fold min infinity x's, where infinity is the max bound of int. Like I'm basically just saying smallest of x's is positive infinity, right? Basically to satisfy our base case, right? So this makes sense to me. The maximum member of an empty list should be infinity, and we can always have infinity when the type that we're dealing with is bounded, and integers are bounded. Right. So here, one of the properties is that the smallest of x's must be less than or equal to every member of x's. Right? This would be a good property. This is a property that's actually helping us try to find mistakes. So I can test that. I can say, okay, given an arbitrary list, make sure that the smallest member of x's is less than or equal to x for every member of x's. I think now this is the Python version. I have to correct this. I knew one thing I did was wrong. Yeah, this should have been a fold. I'll fix that. All right, so let me check. Am I losing my mind today? I doubt this will work. No. Okay, I'll correct that. Okay, what are some other quick checks on smallest that we can do? Pardon me?
The smallest is within the list to start with.
Sure, that smallest is in it?
Yeah.
Something like that? Sure, that would be fine. Here's what I had. I said the smallest between, if you take two lists and you concatenate them, the smallest of that concatenation should be equal to the minimum of the smallest of each of those lists. Make sense? Sort of like a distributive property of smallest. Any other ones that we can come up with? It's like just off the cuff, like if you sort the list in ascending order, its head should be the smallest element. That would be another one. Yeah?
The smallest of a sublist of a list should be
Yeah, the smallest of any sublist of a list should be greater than equal to the smallest of the whole list. Yeah, so all of these are correct. All of these are good ideas, and they're what quick checks are they're not unit tests, right? Not all properties are going to be really good properties, but the idea is if we write like a whole bunch of properties, then maybe we're going to find some case that we like screwed up. Which one's here? Did I just do something the same? Oh, okay. So this is very similar to the one above, except I'm like utilizing smallest twice. I'm saying if I give you the smallest of the concatenation of two lists, that should be smallest of this new list I create, which are just like the two smallest elements from those two lists. So I'm just basically, instead of using this min, using the smallest again, which is a good idea, right? More chances to like find mistakes. So those are a few quick checks on that. Last exercise, so why don't we try to write a bunch of properties? Sort, ascending sort must satisfy. Any ideas here? Involution, right? So sorting once is the same thing as sorting twice. Idempotence. I don't think so. Wait, did I screw up involution? Should this be idempotence? No, this is involution. Oh, yes, sorry. No, yeah, I'm getting confused. Yeah, idempotence is also correct. Okay, hold on. This is not true. Yeah, this should be idempotence, and there should be a sort here. So that's screwed up. I'll fix that. Okay, so here's another one I did where I'm saying the head of the sorted list has to be less than or equal to the minimum of the list. Okay, but there is a trick here, right? So because quick sort or quick check is going to give you empty lists sometime. So I have to make sure to like avoid that. So what I did here is I say, give me two things. Give me an integer, maybe an integer list, and then sort this. So this is going to be guaranteed to be a list of at least one element, right? Which is why I'm able to take its head, right? So, or you could have made your property, check this property, or that the list is empty, and that would have also done it. Just to show you that you can write other functions in your quick check. So I can write an ascending function to check that given a list of inputs, that list of input is indeed in ascending order. And then, of course, here I can say quick check that x is, that a sorted list is indeed ascending. And so that would be a property of being sorted. So, yes?
Is that an ascending function?
Okay, ascending if empty is true.
Shouldn't it be y cons z? Z's at the end?
Which one here?
Yeah, in the ascending, otherwise like you could have 0, 1, 0, 1.
Oh, I forgot. Yeah, no, I have to add y to, yeah. I missed, yeah, y should be there. I should have done a quick check on ascending. Yes, yeah, that should be y. I dumped too many things. I wrote this late last night. Okay. Here's some homework for you to try. So I want you to write quick checks for the following functions. Half of x is equal to x half. So do some quick checks about that. Sort. I want you to do a sort, but I want it to be a custom sort where I give you a custom bigger operation. Right, so I'm saying sort of like if I give you, this may not be like a total sort, maybe a partial sort. Because I can say like sort these strings on their length. Right, or I can say sort these strings by their first character, right? So whenever you sort, you just need to know when given two elements, which one is bigger, right? So that's what that first input there is. It's sort of a custom sort function. Write a quick check for quotient and remainder. This is to emphasize that sometimes you can write a quick check for two things, right? There should be a property about quotient and remainders that's true, that you could quick check on. Here's a question. Are fold R on if I fold the cons operator over something or use list concatenation, are these equal as functions? If not, give a counterexample. And if fn of x's is equal to length of take n of x's, is this equal to n in general? And if not, give a counterexample. So just think about that one for homework. The quick check that you have to do for A2, I asked you to implement average. So I want you to write a couple of non-trivial quick checks for average. That shouldn't be too hard to sort out. Just make sure not to give basically unit tests disguised as quick checks. I don't want you to tell me that the average of a unary list X is X, right? And then do that 100 times. That's sort of too trivial. Don't go anywhere because we're going to do some solutions to assignment 1, not assignment 2. I think I'm through disclosing assignment solutions in class. So you're on reading week next week. And then when you come back, so there's 2 consecutive holiday Mondays, and one of those Mondays is going to be considered a Tuesday. So I think the Monday where we come back, okay, let me just open this, because it's confusing. We lose 1 lesson, but not 2, right? That's why they switched one of the Mondays to Tuesday. So, okay, we are seeing each other after the break. And then we're not seeing each other the week after the break. But you should fact check me on this. This may be wrong. Because not only did this happen, then we had this interruption where it shifted the whole schedule as well. So I'll have to double check. So I'll put out an EdStem, but presuming this is correct, we will see each other the Monday we get back, but not the following Monday. And just be mindful about this in the rest of your classes, that one of the Mondays is Tuesday, so we don't lose 2 consecutive weeks. Oh, also notice, so I changed a little bit here. Functors and applicatives used to be on A2, but because we shifted, I don't think this is going to be enough time to absorb it. Before we had a shift, functors and applicatives happened today, right? So you had all of the reading week to absorb it before the assignment being due. So I took functors and applicatives off assignment 2, and I'm going to be putting them on assignment 3. And because I'm putting them on assignment 3, I'm not going to give you an assignment on parsing and compilers. If I ask you any exam questions on parsing and compilers at all, they're going to be totally trivial. This is going to be the first year I'm going to do parsing and compilers as a topic, so I'm not yet confident enough to give you homework on it yet. But it's still a topic that we should discuss. So just keep that in mind, right? Functors and applicatives are now going to be part of assignment 3, whereas they should have been part of assignment 2. Let's just try to give the chat some love. What's happening here? Chat, you all right? You arguing about what 0 to the power of 0 is? I think we can just sort of ask Haskell and see what it says. Are you too slowly dying inside? The mathematicians are all rolling their eyes at me. This to me is perfectly fine. This doesn't really bother me.
It is 1, isn't it?
Well, according to Haskell, it's 1. But I think according to art, we could. But the problem is, isn't it the case that 0 to anything else essentially is 0?
Yeah, that.
I think the argument here is that exponentiation is essentially a product, and taking something to the exponent 0 is like having the empty product, and the empty product is certainly 1, right? So this I agree with, actually, and that's my argument. Okay, I want to code up one of the solutions from the homework. Let's try mode first, because there is actually a fairly easy way of doing mode. And I want to show you how that happened, or how we can do it there. So one of the solutions I said for mode was getting this intermediate frequency table, but there's an easier way of doing it than that. Did anyone discover the easier? What question do you need the answer to make this question super easy? So this is how I always think about these problems. So you think, let me just get, and I'm just going to put integers in so I don't have to worry about deriving the class instances. So think, what piece of information would I need to make this question super easy. That's too much information. I need, like, I have to say yes because the piece of information I'm seeking is within the piece of information you're determining. But I don't need the whole frequency. I don't need the frequency of every element. I only need to know the frequency of the most frequent element. And I don't even need to know what that element is. Okay, suppose I knew how many times the most frequent element occurs. Okay, let's do that first. Can we count the number of elements in something? How? Okay, I'm going to call it occurrences, right? Let's make occurrences, take a list of integers and return an integer. And occurrences should return the number of times x appears in y's. Return occurrences, number of times x occurs in y's. How can I do that?
You need another int, I think. So you need
Oh, thank you.
and an int.
Yep.
You need a u in the occurrences.
Well, it's not going to work. Like, they need to tell me this, right? It's either they tell me now or it doesn't work at compile time. How can I count the number of times x appears in y's? Length of a filter. Filtering over what? Okay, let me do this. 1 such that x is drawn from y's and, 1 such that y is drawn from y's and x is equal to y. And then I sum over it. Would that work?
Yeah.
Let's see. Occurrences. Am I in the right place? No. Okay. Occurrences of 1 in 1, 1, 2, 3, 1, 1, 7, 4. 1, 2, 3, 4. How many times does 7 occur in here? 1. Okay, so it's easy enough to get like the number of times something occurs in something else. How do I get the maximum occurrences here?
You just have that function, well, the load function, which keeps track of whether the occurrences of the current thing is bigger than or equal to the occurrences of the thing after.
Okay, so, but let's use some higher kinded functions here, right? Because I can, most occurrences, I'll call this occurrences. And it takes an integer and just returns the most occurrences. So I can do something like most occurrences of x's is equal to, and I'm just going to say, well, tell me how many times occurrences for x and x's happens for x drawn from all x's. So this is going to be a list of all of the occurrences, right? And then I just have to find the biggest one, yeah? I don't think, will max work?
Isn't that just a frequency table?
No.
Oh.
Well, it's a frequency table without the associated pairs. Like I just have the numbers. So I'll show you, right? I can say most occurrences.
Yeah.
Okay, well, I'll just do it anyways. Most occurrences. What? Something. Okay, load spam. Most occurrence. Something is not working. Did I not save it? I've been having a lot of problems with my VS Code lately. Load spam. Okay, well that's better than not. What is this complaining about?
I'm checking. You put a list as the output, but you said it would return an int.
Right, this should be this. Okay. So most occurrences. Okay, so that's just simply telling me like 1 occurred twice, 2 occurred once, right? So I guess it is kind of the frequency table. I just didn't call duplicates. Okay, so how do I get, is there a maximum? I always get surprised when there's like not a maximum function. There is no maximum. Okay, so what do I have to fold over this to get the max element? So I need to fold, maybe to the right, maximum over this. Maybe I put a -1, right? Because that's certainly going to act as like negative infinity here. And then I can take this off. Let's see if this works. Okay. Well, it's saying that the most occurrences in that list is 3. And I guess in this case it is 3. Okay, but now that I know what, how many times the most element occurs, how do I find the mode now? Yep.
If the occurrences of that x's is the most occurrences, return that. If it's not, then check for the other part of the list.
Yep. So I can say that I'll just create a temporary variable here, most occurrences in x's. And I have to sort of say, I need a guard. If occurrences of x is equal to t, right? Well, yeah, then that's the mode. Otherwise, I have to be more clever about this. Okay, I'm out of time anyways, but okay, just let me pull up I think there was like one thing I just forgot about. It is here. I have to be so careful. There should be code. Is it in code? Is it in perm Hanoi? Yeah, I know. Mode alternate. Oh yeah, so I had to write it. I had to be a little bit more clever because I had to like put most like outside the helper function. But anyways, it's sort of, you can finish this, but it's essentially like, is this the element that I know how many times this list element occurs? Does it occur as much as the maximum occurrences? No. Okay, then try the next one. Then try the next one. Then try the next one. So this would have been a fairly simple way of implementing mode. Right? So you just needed to think about it. You have to think, what pieces of information do I need to make this question easy? And then write helper functions to get that piece of information. Yeah? Okay, I'll see you. But can someone is anyone going to the tutorial? Could you bring me, please? Because I get quite lost. Okay, thank you, everyone. I'll see you in a couple weeks, I guess. So, huh? Oh, yeah, have a good Easter. To everyone who, yeah. Oh, is that the drinking holiday? Okay, happy Easter, guys. Thanks for showing up, chat. I'll see you later. Bye-bye.